Okay, welcome to our colloquium, electrical engineering colloquium for this week. I'm pleased to welcome our speaker, Dr. Stephen Palm. Steve is from Broadcom, where he's been the last 14 years. And Steve received his bachelor's in electrical engineering from UC Irvine and a master's from CMU and his PhD from University of Tokyo. And he's going to give an interesting talk on home networking today. Steve?
Okay, good morning. So I am going to talk a little bit about home networking and kind of a little bit of a history on that. But really, I'm going to focus on some lessons we can learn from that and kind of the human side and the non-technical side when you're trying to do engineering. So I know you just had some legal advice on how to attend the class and get credit and things. Our corporate lawyers also want to give you a little bit of legal advice. I can summarize this as don't transact Broadcom stock based upon what I do or don't say. So you should be good. You don't need to read all that. All right. So why would anybody even want to do home networking? And this has kind of come out over the last decade or so. And it really was about getting entertainment, all kinds of content, video, audio, whatever, all throughout the home on all kinds of different devices. And so this really what motivates why we would actually go to the effort of figuring out technologies to move data, video, audio throughout the home. So whether it's TVs or your phones or your PCs or printing or what have you, it's really getting that content, and usually entertainment content and sports, but of course it could be educational, throughout the home. So, and a lot of that comes from kind of the way the architecture was of getting content throughout the home. In the good old days, you know, maybe you're a cable or a satellite guy, they would give you a set-top box, some big box for every single TV in your house. And if you had any other devices like cell phones or tablets or PCs, they didn't have a way of getting TV onto that. Now remember, this is 10, 15 years ago, so it's very different than it is now, but this is really what drove home networking. And so they really were trying to look for architectures where you bring some data into the home, maybe through some kind of gateway, and then you send it to all the devices in the home, laptops, tablets, et cetera, through some industry standards. And the number one thing you had to have was communication. How do you move the bits, the data, the files from outside the home throughout the home? And there's some other things that were needed as well too. How do you protect the content? How do you make sure that the quality of service is good? Even now, there's a lot of things where we're concerned about saving energy. So it's not just getting the bits there, but getting them there efficiently. And diagnostics. So there's a whole bunch of other things that are also required for getting the technologies throughout the home. So over the years, there's been a plethora of all kinds of technologies that people have tried in order to get those bits, those files throughout your home. I'm not going to talk about all of them, but there were some that just failed pretty quickly. They just had technology problems. They had acceptance problems. So I'll focus on a few and just kind of look at some of the things that made them good and some of the things that made them bad as well. So really, kind of in the 70s, the first home networking used the electrical outlets, right? That's what people had. It was ubiquitous inside the home. And they built these little modules, and you could flip on your lights on or off, maybe turn on your hi-fi or stereo back in those days. And it had a screaming data rate of around 20 bits per second, barely moving anything, right? So. But that was all it was needed to find the address of a device and turn a light on or dim it or something like that. So obviously, those kinds of data rates really aren't going to provide entertainment quality, but that's where it really all started inside the home, just a few bits. So a lot of times, people think, well, hey, let's just use Ethernet. Ethernet's been around 40 years now. They just celebrated their anniversary last year of 40 years. And it was very popular in businesses. First started with the very thick coax and then transitioned into twisted pair. But again, we're trying to move data and things around the home, and there was a couple of issues of using Ethernet inside the home. First, it really took administrators, someone who really knew what they were doing to kind of manage it and also to install it. And it was kind of a complicated wiring job, and maybe you'd have to go to some wiring closet or something like that. And so it just was not the kind of technology that could work well inside the home. Worked very well in a business, but just was not well suited for the home. And so it never was a popular whole home technology. So obviously you see a lot of Ethernet jacks on a lot of devices these days, but it's pretty rare to see Ethernet going from one home to another, from one room to another. And I think generally in the US now, it's maybe about 5 or 10% of the homes might have Ethernet wiring already pre-installed. But if you don't have it, it's a pretty big challenge to get it installed. So again, while it was popular inside the businesses, it was not really a technology for inside the home. So the next technology that was actually really designed for the home was called home P&A, and the P stood for phone line, because that's originally where the technology was developed. So if you had a home, and this is actually the slide I dragged out from the year 2000, if you had a home, in those days, you were just now starting to get DSL modems, you're just starting to get cable modems, and of course, you could bring your TV in but to watch content, but you also had your computer. And perhaps none of you had to deal with it, but if you remember, those were AOL, dial-up modems. You're always having to use the phone lines to connect up your computer. You plug the phone jack into your computer. You can't even buy a computer with a phone jack in it today, but that's what was very ubiquitous 10, 15 years ago. And so the idea was, well, if you're already using the phone lines to connect and get your broadband by dialing up to a server, well, maybe you could also use those phone lines inside your home as a data networking. They were already there. You didn't have to have anyone come install it. You could just simply plug it into the device. And so the idea was to use all the rest of the phone jacks in your home, and you could connect voice over IP phones, extra televisions, and things like that. I remember in those days, it wasn't HD, it wasn't even Ultra HD, it was standard definition, very low tube TVs. Again, I know it's maybe pretty foreign, but it wasn't that long ago for some of us. And so, and the way the home P&A worked is your normal phone service took up a little bit of spectrum, usually up to about 4 kilohertz. Then, as I mentioned, DSL was becoming popular at the time. And so your phone company was providing broadband service. And so that, in those cases, it would definitely take up some spectrum up to about 1 or 2 megahertz. And then they separated out. And then the home P&A signal would be above that. And part of the problem was to separate so that the signals from the home P&A didn't actually conflict or interfere with the signals on the DSL or on the POTS line. But just very simply plug in to the phone jacks to get your data networking service. Now, one of the biggest differences between Cat5 and Ethernet, Cat5 and Ethernet and home using the phone lines is that the reliability and the data rates were not guaranteed. There were other signals that were already on the phone lines. Perhaps it was DSL, perhaps it was just interference from radio waves. And the home networking, in this case the home P&A, had to deal with those external signals. And so it was an adaptive process, and generally, in about, they did some field trials, and about 50% of the homes, they could get about 10 megabits. And 10 megabits in those days was good enough for maybe 1, maybe 2 standard definition television streams. So that was okay. But the problem with it, if it only got about that data rate for about half the homes, service providers, your cable company or your telephone company, was worried that, well, I can't install in half the homes, and I don't know which half of the homes it's actually going to work in. So, I need a better install rate. And so they were always looking for something around 98, 99. They really wanted 100% of the time that if they install this technology, I'm going to have enough throughput in order to deliver 1 or 2 TV channels. But the problem is, as you can see here, is at 96%, well, you could guarantee pretty much 6 megabits per second. If you wanted a 99% guarantee that a particular data rate was going to work, you're probably down in the 3 or 2 megabits per second range. And so that really wasn't enough to say I can guarantee getting a HD signal, an SD signal throughout the home. I need to get video throughout the home without worrying about, is it going to work? Do I have to send in a technician to go figure out if it's working correctly or go fix it or things like that? So really, they were always searching for profitability by looking for it really has to work 99 to 100% of the time. So just a little bit on the marketing side, but in those days, goals were to deploy 1 million or 2 million devices. If you were deploying that number of devices, that was considered successful. And of course, today we'll see that the numbers are much, much larger than that. And the vision then, of course, this is from the perspective of the people who are selling phone line, is phone line's going to win. Remember, these slides were from 2000. And wireless, who wants wireless? It's not going to be very successful. Nobody wants Wi-Fi. It doesn't work that well. And yeah, there'll be some Ethernet, right? This is the kind of perspective that people started from. And it kind of blinds them a little bit on some of the requirements that were actually needed. So one kind of anecdotal part of this was, so that, again, in 2000, people were trying to sell this technology, this phone line networking technology. And there's a couple gotchas that happened, in addition to not being able to reliably give the bandwidth to all the outlets, is that it's really hard to see because it's low res, but the boxes were all labeled 10 megabits per second. And this is the same time as Ethernet was 10 megabits per second. And the jack for the phone jack and the jack for the Ethernet jack, they look pretty similar. The Ethernet jack a little bit bigger. So people kind of look at the box. They didn't really know. This is around 2000, 2001. They didn't really know what the technology was. They kind of maybe knew something about Ethernet if they'd seen it at work. And so they get this home. They try to plug it in. It doesn't work, right? They think it's Ethernet, and it's not. So that was part of the confusion. And it was just too hard for consumers to realize the differences between the technology they might have known, Ethernet, and this new technology. So that was kind of the other aspect. Just besides being confusing, it really required a huge education process. You saw, you see here there's these displays in CompUSA and other stores, but it's still very, very hard to educate users on how to use this technology. So another idea, of course, remember I started back with X10, that 20 bits per second technology, was, okay, let's try again. Let's do a little bit better. Let's use a little bit more spectrum and have some devices that we can plug into the wall again and use wiring. Because again, the problem with Ethernet was it was very hard to wire up. Phone line was already there, so you didn't have to do any wiring. Of course, the electrical is already there, so you don't have to do any wiring. So really, the idea was to find a no new wires technology, and so of course, reuse the existing wires in the home, and this would be the electrical wires. So a little different problem happened with the power line is a couple of different groups of people that thought that this was a great idea, but they couldn't agree. There was lots of competition on specifications. So there's kind of the incumbent guy who had their technology, and then there was a group from Japan that was kind of based with Panasonic. There was a group from Europe. They all got kind of regional and said, hey, we'll go figure this out. And later there was another group called G.HN, and basically you had 4 or 5 groups all fighting to do the exact same thing with technologies that didn't interoperate. And so the the service providers and the public got very confused. People were fighting. This is back like fighting Betamax versus VHS videotapes or any other format kinds of wars. And so what people normally do when the industry guys are fighting are keep their money in their pockets. And so because of the diversity, because of the groups that didn't interoperate, it always was kind of a drag on the technologies. And as they started to try and improve the technology with Powerline, kind of the second generation version didn't interoperate with the previous version. You couldn't have both sets of technologies on the same wires. So that was also very complicated for folks. If they had some old technology, they brought some new technology, none of it worked together. So really the lesson in Powerline was if you don't have ubiquitous standards and they don't interoperate and they are not backwards interoperable, it really is a drag on the technology, no matter how good the technology is. So after that second generation, when they went to third generation, they did kind of take that lesson to heart. So they had a higher speed version and a lower speed version that all interoperated and worked very nicely. But kind of like I was showing on the phone line side, the data rates you could get, if you were really lucky, you could get 200, 500 megabits per second actual throughput, but that's in a very small percentage of the actual homes. It's great in the laboratory, it's great for showing experiments, but when you actually deploy in actual homes, those were in the range of 5 to 10% of the homes that could actually reach that. Now, if you go back up to here where you're trying to reach as close to 100% as possible, then you can see that the data rates, well, in the previous generation, were about 10 megabits per second, and now are about 20 megabits per second. So enough now with the current coding technologies, you can get 2 or 3 high-definition streams, the typical television of today, and so that's enough. And you can see, even at those modest rates, if doubling the throughput actually makes a large difference, because that allows an additional channel, so you could have 2 or possibly 3 channels inside the home. But again, often when these are advertised, for the HomePlug AV2, the advertised data rate is 1.6 gigabits per second. The issue comes with overhead, with retransmission, dealing with all the interference that is on these electrical wires. You have all kinds of motors, refrigerators, CFL light bulbs, all these kinds of things inject noise into the power line. And so it was not really designed to have data communication signals. And this is why you see such a disparity between the very high throughput of the underlying fire rate and the actual throughput that you can get with these technologies. So Wi-Fi. You may or not have heard about the phone line or HomePlug, but obviously you've heard of Wi-Fi. So Wi-Fi first generation around 97. In those days, it was 1 megabit per second, 2 megabit per second. That was the fire rate. The actual throughput was lower, just like all these technologies. It was kind of an industrial usage application. People weren't using it in their homes. But then around 11B, around 99, 2000, it started being used a little bit more in the home. Apple brought out their airport products and really tried to get people to use home networking inside their home with the broadband. But it was pretty expensive at the time. The Airport Express was like $300. The cards were $100. But people were actually starting to use it. And right around 2002, really the third generation of Wi-Fi came out. It was called 802.11g. And the advertised data rate was 54 megabits per second. But like I say, with interference and things like that, people are getting 5 or 10 megabits per second in that kind of range. And it kind of moved from just kind of simple email, the previous generation, just not moving that much around, that you could actually have a pretty rich web experience. And the other thing that happened at this time is a huge marketing campaign. So Intel went out and spent a $500 million telling everybody, you need Wi-Fi in your laptop. So the upshot was, you can't buy a laptop today that doesn't have Wi-Fi. Everybody got it in their minds, I need Wi-Fi, I got to go buy Wi-Fi. They had television ads, all kinds of things. But literally, it took $500 million to go tell people, to educate consumers, this is the technology, this is how it works, and you need it. So it actually took someone spending a lot of money in order to help educate to get the technology, even though it was good technology, but to get the technology into the minds of folks. So the next generation of Wi-Fi actually took quite a number of years. Before, it was kind of like 2-3 years before that, in between generations. And kind of in the voice band modem days, it was generally every 2 or 3 years when a new technology, you generally are trying to double the speed at those times. But 802.11n, in the standards group in those days, IEEE, just a lot of people had piled in. And now there was 1,000 engineers and whatnot trying to develop something. And whenever you get a group that huge, it's actually pretty hard to get everybody to agree. Because in IEEE, you need 75% of the people to agree, yep, we're done, yes, we agree that this is the technology. And trying to get 750 engineers out of 1,000 to agree on the technology is actually very challenging. And so the actual standard came out in 2007, but products started shipping around 2004, 2005. So again, part of it is getting it done, but part of it is getting it done in a timely manner. If you miss your marketing opportunity window, the technology can be a failure or just not bloom into success. And so part of it is, in addition to making sure the technology is good, you have to make sure that the technology is timely as well. There again, the data rates are increasing. The highest throughput that people are advertising is 600 megabits per second. But the actual throughput you're getting are much less. And then about a year or 2 years ago, and actually people started announcing 5th generation projects based on 802.11ac from IEEE, and going into the gigabit range of the actual PHY rates. So again, what's advertised and what you actually get is often a little bit different. So this is very hard to read, but the idea is that down in the corner here, in an office environment, a Wi-Fi access point was set up. And you probably already know this by experience, but your data rate really depends on where you are and how far away you are from the access point. And you know, when you're really nearby, even though it advertised a gigabit, your actual throughput's in the 200 to 300 megabits per second range. And as you start clocking around here, you see it dipping down under 200, and even some here down as low as 8 or 10 megabits per second. Basically, the actual throughput of technology is 3 or 4 generations back. And so while Wi-Fi can be very good, and it's great that it works with the mobile devices, it, like everything else, is challenged by the environment. And so some of the, you know, there's the other Wi-Fi devices that also interfere, because they're all using the same channels, they're all using the same frequency spectrum. And so they're competing with one another to actually send the data. And plus, all the Wi-Fi bands are either in industrial bands or basically dirty bands. The Wi-Fi 2.4 band is actually in the same band as microwave ovens. That's why it was given away, so anybody could use it without a license. So when your microwave oven cranks up, your Wi-Fi throughputs will go down. Similar to 5 gigahertz, it shares with other technologies as well. So again, all those technologies trying to not put new wires inside the home. So we'll look at another technology here. This is called MoCA. And it basically used the coaxial wiring that you already had in your home, typically through your cable television provider or your satellite provider. And the idea was that you would take that coax, and normally the signals would come in, from the broadband provider. The cable would come into your home. You'd have a couple of splitters in order to help isolate between the different televisions in your home. Maybe you have a couple of splitters in your home, and then these devices at the end would be televisions. And the whole idea when the system was developed, that you would actually isolate between these end devices, and you didn't want them to interfere with each other, and basically because all the signals were only going downstream to your television set. Well, the idea, if you're going to reuse the coax, was, well, you may have devices, set-top boxes, or computers, or things at these endpoints, and you want to actually transmit between those two endpoints. So you actually had to go through the splitter that was designed that you weren't supposed to actually get through. Typically, they were trying to have at least 30 dB of attenuation to block out between the ports. The other thing that could happen is as you start transmitting signals up into those splitters, obviously there's going to be some return loss, there's going to be some echo, various factors that really weren't in part of the design. The other part was you had to stay out of the way of the existing signals, so you were at higher frequencies than these components were designed for. And so what really happens is the frequency response really varied as a function of frequency. You can see you know, some pretty deep nulls of 20 or 30 dB, which has a pretty strong effect on your ability to actually receive that signal accurately. And depending on the length of that, of the splitters or the reflections, really change the characteristics. Kind of the black dotted line shows with 5 meters and 100 meters with the green. And you can see the number of nulls and the attenuation had a very different effect. So you never knew ahead of time, well, when you're designing these devices, what actual signals you would see on the coax inside the home. And so you had to be designed the products to be very, very robust on that. So the other aspect too is that some of these reflections, the signals would actually be stronger than and arrive before the actual signal arrived. I was starting to mention you have to share the spectrum with other services because you're trying to reuse the coax. I'm showing the satellite signals up here. They typically were at the higher frequencies, and so MoCA would try and be below. But sometimes there'd be other signals, and I just kind of gave a relative showing of where the power line. Generally, the lower in the frequencies, there tends to be a lot more interference that couples in, especially on the power line and even on the coax. And so finding not occupied frequencies and where the interference is not bad is actually pretty challenging. And so MoCA was also designed to work with different channels, which I'm showing here, in order to find the best performance. The other thing you can kind of see here is that you have satellite and cable, and if you actually had those on the same coax, that didn't really leave much room at all to put the MoCA signals. So even though the coax was an extremely good medium, generally less interference than the power line, it still did suffer from some interference, but it did give much better data rates. And kind of the other technologies that I'll also mention before, besides the physical layer, how they actually put packets onto the wire differed. So a lot of this goes back to Ethernet, whereas it was a kind of a collision avoidance situation. You may have a couple of different devices on the network, and there wasn't anyone going around saying, hey, you transmit first, and then you transmit. They would both try and transmit, perhaps at the same time. And if they did detect a collision, then they would back off a random amount of time, and then another one would try again. So it was good that it didn't require a central controller, but what happened is when you actually had to send some data, it would actually have to back off, and you never knew the amount of latency before you could actually transmit the data. Now, when you're reading email or any non-latency, sensitive services, that was fine. But as we started to move to video or voice, where if you start delaying packets, the voice sounds bad, the picture breaks up, things like that, that was completely unacceptable. So the technologies that were okay for data transmission were not going to be sufficient for transmitting video and audio inside the home. So one of the other aspects that MoCA really had to go change was, instead of using the basic Ethernet technologies that have been used on phone line and power line and Wi-Fi, is to go to a controlled approach where devices request to transmit, and then the central network controller would actually grant times that they could transmit. And the whole idea was to get a handle on latency, so you'd have very good quality of service. So, of course, a couple of the generations, everybody's trying to increase the speeds. It went from about 100 to 200 megabits per second actual throughput. And then the latest generation is about 400 or 500 megabits per second. Those are the actual throughputs. The underlying PHY rates are about 700 megabits per second. And so when you have several hundred megabits per second actual throughput, that's easy to send multiple high definition television streams, and now the ultra high definitions. The other thing that really kind of crept up was job number one is getting throughput throughout the entire house. But in the meantime, we've had a lot of folks become very interested in conserving energy inside our homes and businesses. And networking components and your consumer electronics devices actually do consume a fair amount of the energy you have in the home. And so there were some studies done, and like when you thought you were turning off the set-top box or your consumer electronics device, you're just turning off the light, you were still actually consuming the full power. A number of folks said, hey, we've got to do better. We can engineer better than this to save power. So almost all of these second generation technologies really had to go beyond getting throughput to all the devices. But when you didn't need all that throughput, to scale back and have a lot less power that's being consumed. And so that was really another part that we've been working on the last 5 years. So one of the nicer things about MoCA, because it is a nicer medium, is this line here shows the actual PHY rate, but literally in 100% of the homes, you can get somewhere between 75 and 100 megabits per second. So the part about that was it made it very comfortable for the service providers, your cable TV guy, your satellite guy, to say, this is the technology that I can install, and I will know I'm not going to have to go fiddle around, go back in, and if it doesn't work. And so as it turns out, MoCA is the technology that is very, very widely deployed today in the US for many of the technologies. So if you have like a DirecTV Genie service or a cable, and they have multiple set-top boxes, they're all using this MoCA technology right now. So part of the things I mentioned, some of the pluses and minuses of the different technologies, even with the MoCA, which is pretty easy to install if you don't already have it and has very good data rates, well, you're not really going to screw a cable into your phone or your tablet or something. That technology doesn't work. And then maybe you want to enjoy some entertainment, just outside on the patio or something like that. There again, you're not going to have a cable. So what it really comes down to is no one technology solves all of the home networking problems, right? So there's some data here showing, where there are coaxial outlets in different rooms. Some rooms, living room, family room, very high percentage, 81%. But again, that's not those 100% kinds of numbers that the service providers or you want. You always want it to work. Same with phone outlets or things like that. And so no one technology has won on home networking. And so this has still been a problem that's been challenging us. And so we started thinking about, well, we have a lot of good technologies, and we don't really want to start from scratch. There's a couple billion Wi-Fi devices out there. There's hundreds of millions of these other technologies out there. People don't want to throw this out. These are the technologies we have. How can we reuse those technologies, kind of put them together in a hybrid, and take the advantages of those technologies and kind of get rid of some of those detriments that I was mentioning about, either the interference or things like that. And because sometimes it works good in a room, a technology, and sometimes a different technology works better in a different room. And you never know at install time which are those. So the technology should really figure that out for you. Which of the technologies work the best? And so, and the idea would be you put in multiple technologies. Your device would have both Wi-Fi and Ethernet or MoCA. And depending on which had the best path, that would be the technology you use for that device, and the technology would automatically figure it out. So, and the other part, besides the high data rates, service providers are kind of lazy. Basically, their model would be, you give me a lot of money, and I don't want to do much work. I don't want to put in much equipment. I don't want to send people to your house. I don't want you to call me, because all those things cost money, and I don't make as much money. And so they've really been pushing not just high throughput and not just power savings, but it has to be easy to install. And when Wi-Fi first came out, you had to enter network names, and people called them SSIDs, and you had to enter passwords, and people didn't do it, and people got hacked. And so it was just too complicated. So all the technologies now have been really trying to simplify the setup, and basically come down to models like, hey, if I can just push a button on a device and push a button on another device and connect them up securely, that's really the easiest for folks. Now, of course, you want to do it in such a way as not people randomly or your neighbor randomly pushing the button, but within a certain amount of time, and some cryptographic technologies to make sure that it's actually you hooking it up. So that was one of the things that 1905 in hybrid networking tried to do, is unify it. It shouldn't matter whether I have MoCA or Wi-Fi or any of these technologies. I want to hook them all up. Another part is, well, we like Wi-Fi, but remember that chart of the office where Wi-Fi is good in some areas and not other areas? If I could add more Wi-Fi in the home, that will probably help. But how do I get the Wi-Fi from one part of the home to the other? Well, this is where the technologies like home plug for the power line or MoCA are very handy. But there again, people don't want to spend a lot of time to install it. So another thing that was, besides connecting up the devices securely, if you plugged in a second Wi-Fi access point inside your home, you want it to be the same network configuration as your original Wi-Fi access point. And so to automatically copy that configuration over, so there again, the user doesn't have to do much thinking in order to get the technology up and running in their home. And the other part too is in the past, when service providers were providing these set-top boxes and things, they actually kind of control these boxes. They know a lot of information. They can get a lot of diagnostics out of them if something's going bad. But generally, the home networks, they had no information. And people would call up and say, hey, my TV's not working. And they have no idea, well, is there a Wi-Fi problem? Did they forget to plug something in, or things like that? And so there's been a lot of requests for understanding the configuration of the home network, bringing that back up to the service provider. So in a sense, kind of the next generation of technology wasn't about the highest or fastest, but really easiest, how to make it simple for users and for the people selling the services in order to get it functioning very, very easily inside the home, thereby, as most of these companies want to do, maximize profit. So that's some very recent work, and it's actually work in progress that you can find out. Of course, all these slides will be available. And so a lot of that has to do with kind of home networking. A lot of that has been kind of solved, but now we're kind of entering in a new era. It's been around a year or two. It goes by a lot of names. Some people call it the Internet of Things, which is always very nebulous. A popular term before that was machine-to-machine communication. A new buzzword now is wearables. And really, when those technologies I talked about for home were about, kind of getting information and entertainment to people, to humans, right? Now this is a little bit more about, well, to help the humans, we want to have a lot more communication between all the devices in your home. Or in your car or wherever, right? So people are wearing these fitness bands and things like that. And they're all, again, essentially relying on local area technologies, a little bit different than home networking. But a lot of the things that challenged home networking are being played out again in this Internet of Things and machine-to-machine. And people get a little bit interested in the fitness, they try and do it, and then they kind of give up on it. And there's even some companies recently that kind of laid off just a few days ago their entire teams working on these. And there's a lot of standards and a lot of competition. Again, all of these sound very familiar to some of the problems we were talking about in communication. Multiple non-interoperating systems, and just kind of not feeding on the previous generation technologies. And I'm encouraging, because obviously a lot of views, some of these will take a few years but to play out, but some of you will actually be involved in bringing those generation into fruition. And so I just want to kind of focus on a couple of things at the end. Always make sure, if you're building a communication system, make sure you can talk to the old devices. Don't assume people will throw everything out. It's great the sales guys in your company might appreciate that, but don't assume people are going to throw it out. They're going to have devices. You do need to communicate with those existing devices. And so that leads to more of an evolution instead of a revolution. I know it's always exciting to be change and very different than before, and some of the underlying technologies do that, but they always have to make sure that you're bringing the previous generation with you. And this part about the human factor, it's really about, it's not just having the best numbers on the paper. It's not about having the highest throughput or the percentage. It actually has to work for people. It actually has to be acceptable. And part of that is the usability, and part of that is the understanding. If you're introducing new technologies and folks just don't have the underlying grasp of how they would use it, it becomes a challenge in that area. And so really, as you move in, and if you're working in communication systems, I would definitely encourage you to consider some of these factors on that. So thank you for listening on things. I think we do have some time for questions and things like that. And I'd welcome any questions either on the technology side or anything on that. Thank you.
Do we have any questions from the audience?
And don't be shy. There are no dumb questions.
Yes.
Everybody is talking about IoT or end-to-end.
Right.
And at the same time, everybody is jumping into, currently a lot of the countries are jumping into like the 4G technology, like either LTE advanced or WiMAX. And people are also talking about 5G. Do you think when we are using those 4G technology, no matter LTE advanced or WiMAX, end-to-end will follow this standard, or end-to-end will come up with their own standard for 5G purpose?
Right. So just kind of repeating your question, you're talking about, there are a lot of people are talking about Internet of Things, right? But then there's also 4G and 5G, LTE, all these broadband communication systems. So one of the big disparities is 4G and LTE and 3G, all of those take a lot of power. So a lot of, especially the wearables, right? The very small battery, they're hoping it lasts many years, coin cell battery, the power doesn't add up. And so almost all the time, those low power requirement devices will have to have some gateway before they go to 4G and other technologies. So that's a lot where the home network comes in, because you'll definitely see several of your devices, your phones, your TVs, et cetera, as being gateways to those internet sensors. So whether it's sensors on your body or sensors on your windows, for security or things like that. So part of that was they won't be directly connected through 4G. They'll have to go through gateways. The other part of your question was, what will be how they actually talk? And I didn't actually speak too much. I spent more on the lower layers. But in order to get that entertainment that I was talking about, there was technologies called Digital Living Network Alliance, DLNA, that were used. And this is actually the big challenge for Internet of Things right now. How do you actually collect all that data and use it? So I drive my family crazy, but I have all these air quality sensors, windows sensors. I have a water sensor to know if my lawn needs to be watered. I have all these sensors, and they all came with their own app, but it's very, very hard to collect those bits of information into one cohesive database to actually use. And so that's the so-called big data problem that's happening now. So this is actually an area of active standards development to figure out how do you get all these devices to not only just talk to each other by communication, but collect their data in a format that people can actually use it. So this actually is the challenge right now. And like I say, we had some of the technologies for doing the entertainment in the home, but how did you do the security, protect the content, all those kinds of factors is really what took an extra 5 years to solve those problems. So that is an active area right now. Excellent question.
Any other questions? Can you elaborate a little more on the security aspects of the hybrid networks that you worked on?
Yes, so just elaborating a little bit on the security aspects. So, kind of in the first days, as I mentioned, people didn't really want to set up security. It was hard, passwords and things like that. And so Wi-Fi developed a technology called Wi-Fi Protected Setup, and Powerline did as well. And basically, there's a couple factors. And a lot of people do try to use pins as kind of a number just to, in lieu of a complicated password. But kind of for most folks, they have trouble figuring out the number, which number is it on the, on the bottom of the box. And so that's why kind of people went to the push button approach. Now on the hybrid side, one of the important aspects of the hybrid was don't reinvent all those technologies you're using underneath, whether it's MoCA or Wi-Fi. And so now Wi-Fi and HomePlug already have kind of their own security mechanisms. And so the hybrid said, hey, we're not going to reinvent that because there's always security hacking issues like Heartbleed, if you've been reading about lately. And so it basically sends a virtual push button to all the devices to connect them all at once. So they rely on their own mechanisms, so we didn't have to reinvent something. So it's always a challenge when you want to invent security protocols, and as folks at OpenSSL are finding out now.
Any other questions?
Okay.
Okay.
Well, I'm around afterwards, and if people have any questions about Broadcom, please feel free to stop by. Thank you.
Thanks.